Welcome back to the Energy Conversion Lectures. This lecture and the few coming lectures will focus on the principles of the electromechanical energy conversion and the analysis of devices that accomplish the energy conversion. In general, electromechanical energy conversion systems are used to convert electrical energy input into mechanical energy output, and vice versa. If the conversion of energy is from the electrical energy to mechanical energy, we call it motoring operation. If the conversion is from mechanical energy to electrical energy, we call it generation operation. Electromechanical energy conversion systems can be classified into two systems based on motion type. These two systems are linear motion systems and rotating motion systems. Linear motion systems or devices convert electrical energy represented by the voltage V and the current I to mechanical energy represented by the displacement X and linear mechanical force Fm. Rotational movement systems convert electrical energy represented by the voltage V and the current I to rotational movement angle theta and rotational torque Tm. The energy conversion process of these systems take place through a medium of magnetic field or coupling field. In other words, the interaction between the electrical input and the mechanical output occurs through a medium of magnetic field stored energy. This will be explained in details through this lecture. Just to mention here that the goal of this lecture and the following few lectures is to establish the foundation of electromechanical systems and mainly derive expressions for the linear force Fm and the rotational torque Tm for these systems. Electromechanical energy conversion systems can also be classified into two categories based on the number of excitation currents or number of coils. These categories are single excited systems and multiple excited systems. Single excited system means that the system has only one source of excitation or one coil as shown in this simplified actuator. In general, the actuator term represents most of the linear motion devices or translational motion devices. These devices called linear motion devices because their moving part moves linearly, such as solenoid, relay, and electromagnet. These devices, also called linear force producing devices, simply because they produce linear force. Basically, actuators are not continuous energy conversion devices. That means actuators perform the energy conversion or the mechanical movement only once during the excitation. In other words, the moving part of the actuator moves and then stops during the excitation. Once the excitation is removed, the actuator moving part resets to its original state. It is very interesting to know that there are some devices called MEMS which are in micro size that share same concept of electromechanical energy conversion systems. The applications of these MEMS are medical, biomedical, aerospace, automotive, and manufacturing applications. Multiple excited systems means that the system has more than one excitation source or more than one excitation coil as shown in this figure. This figure shows simplified rotating machine which represents the fundamental concept of almost all the electrical machines. This simplified rotating machine has two sources or two excitation coils. Basically, this doubly excited rotating machine represents the concept of almost all the rotating machines. Rotating electrical machines are continuous energy conversion machines. That means the process of energy conversion is continuously happens during the operation or excitation. In other words, the machine moves or rotates continuously during the excitation. Both the single excited systems and multiple excited systems share same energy conversion process concepts. Therefore, for now, let's focus on the single excited systems as an example to explain some basic principles and terms. This single excited device or linear motion device consists of one coil, C-shaped fixed part made from magnetic material or ferromagnetic material, and moving part also made from magnetic material. The moving part connected to fixed frame through a mechanical spring. Since electromechanical energy devices and machines perform some movement, therefore these devices must have some air gaps to allow for the movement. This air gap represents an important part in the electromechanical energy conversion systems. In general, this electromechanical energy conversion system or any electromechanical energy conversion system can be represented by three systems. The first system is the electrical system, which represents the electrical source, the resistance R, and the coil. The second system is the coupling field, which represents the magnetic field that flow through the C-shape and cross the moving part through the air gap. The third system is the mechanical system, which represents the moving part and the mechanical spring. So the electrical input energy will be entered to the electrical system and then will be entered to the magnetic coupling field, which some of this energy will be transferred to mechanical energy and the rest will be stored as a magnetic field energy. It is very clear that the energy direction is transferred from the electrical input energy to mechanical output energy. Note that the direction of this energy conversion process can also be operated in reverse way. That means if we feed the electromechanical energy system by mechanical energy, the mechanical energy will enter the coupling field and then will be transferred from the coupling field to the electrical system as electrical energy. Basically, the coupling field will serve as conduit between the electrical energy and the mechanical energy. In general, operation that convert the electrical to mechanical energy through the coupling field is called motoring operation, and the system that convert the mechanical energy to electrical energy through the coupling field is called generation operation. In principle, same electromechanical energy conversion system or device can work either in motoring operation or in generation operation. In practice, all these three systems experience some losses. These losses are the electrical system loss, coupling field system loss, and the mechanical system loss. As you can see, these losses are subtracted from the main energy flow or from the input energy. The electrical system loss results due to flow of current through the electrical windings. The electrical system loss represented by I square R. The mechanical system loss is usually due to mechanical friction loss and windage loss. In case of magnetic coupling field system, the loss is due to magnetic core loss such as hysteresis and eddy current loss that we covered in the first chapter. Basically, since there is no ideal magnetic material, the hysteresis effect or loss will be always there. Also, we will see later that the magnetic core will experience changes in magnetic field during the process of the electromechanical energy conversion. Therefore, eddy current loss will be produced and will be always there. All these losses are dissipated as a heat and they are not contributing to the energy conversion process. Therefore, these losses will be ignored during the mathematical derivation. One can ask what happens if we have some leakage magnetic field, which is usually the case in practice. Should we consider the leakage field as a loss? Basically, leakage magnetic field can be considered as type of stored energy, and this energy does not dissipate as a heat, so it is not a loss. However, this leakage field energy does not contribute to the electromechanical energy conversion because leakage field does not cross the air gap to the moving part. Leakage field usually causing a voltage drop to the applied voltage and can be modeled as leakage inductance in series with the resistance R. In summary, all the energy losses and the leakage field energy will be ignored during the mathematical derivation because they are not contributing to the process of the electromechanical energy conversion. In other words, we will assume that the electromechanical system is lossless during the mathematical derivation. Now, if we compare this actuator or any electromechanical energy conversion device with one of the static magnetic circuits such as a transformer, you will notice that the static machine has no air gap. However, in practice, these magnetic circuits do have some air gap. Usually, these static devices built with more than one piece to allow for inserting the coils to these machines as shown. These air gaps are very small comparing with the air gaps of the electromechanical energy conversion systems. Note that we call the transformer static machine because they have no moving parts. So now we know that the electromechanical energy systems have some large or considerable air gap length in their systems. Any magnetic circuit with large air gap length means it requires larger magnetizing current, also will have more linear magnetic characteristics comparing with system with a small air gap. System with a small air gap requires a smaller magnetizing current and have more non-linear magnetic characteristics. Let's explain this concept with little more details. In general, the air gap has large reluctance because it has very small permeability mu0, while the magnetic material or magnetic core has a small reluctance because it has high permeability mu-c. Now, magnetic circuit that has very small air gap length comparing to magnetic core, the magnetic core going to be dominant and therefore the magnetic circuit will have high permeability and low reluctance. That means the magnetic circuit will be magnetized and saturated easily with a small excitation current or magnetizing current. However, when the magnetic circuit has large air gap length, the air gap going to be dominant, and therefore the magnetic circuit will have low permeability and high reluctance. Therefore, magnetic circuit with large air gap requires high excitation current or magnetizing current to be magnetized and saturated. This figure shows the psi-I characteristics of two magnetic circuits, one with small air gap and the other with large air gap. Now, if we want to magnetize the two magnetic circuits to certain magnetic field linkage psi1, the magnetic circuit with a small air gap will require small current I1, while the magnetic circuit that have large air gap will require larger current I2 to achieve the required magnetic field linkage psi1. The second point to notice is that the magnetic circuit with a small air gap will have more nonlinear characteristics because it reaches the saturation easily, while the magnetic circuit with large air gap will have more linear characteristics because it is hard to be saturated. It should be noted here that the magnetizing current and the required magnetic field psi1 are usually decided within the design stage of the magnetic circuit. The magnetic circuit or system that have small air gap can be called nonlinear magnetic system, and the system that have large air gap can be called linear magnetic system. Now, if we have a magnetic circuit with large air gap and then the air gap becomes smaller, the curve of this magnetic circuit will move as shown. Now let's get back to the relay electromechanical system shown and try to understand the principle of its operation. If the system is excited by a DC voltage V, a current I will be drawn and pass through the coil. The change of the current I will cause a change in magnetic field. This magnetic field will magnetize the core and then attract the moving part toward the C-shaped magnet by certain linear force Fm. This force can also be called field force because it is generated as a result of the magnetic field. Note that the current I should be strong enough to overcome the mechanical spring mechanism and be able to pull the moving part toward the C-shaped fixed part. Now let's pay attention to the following. As the moving part gets attracted and started to move and approaches the C shape, the air gap length becomes smaller, the reluctance becomes smaller, and therefore the inductance of the magnetic circuit becomes larger. Note that the air gap length, reluctance, and the inductance have been represented as a function of x because they change as a function of the air gap distance x. This change of inductance because of the movement causes change in the current I and hence rate change or increase in the magnetic field linkage psi. Also, we can say the following. As the reluctance becomes smaller, the magnetic field phi becomes larger. This increase or rate change in magnetic field phi or magnetic field linkage psi is nothing but increase in the magnetic field stored energy. To summarize the process, we can say that when we applied the electrical input voltage V, we got mechanical movement and increase in the magnetic field stored energy. Let me know if you have any question. Also, Make sure to subscribe to this channel so you do not miss any lecture. Thanks for listening. I'm Ihsan al-Nabi, and it was a pleasure sharing this lecture with you. Thank you.